Hello everyone, this is N.K. Pandey. Today we will look into the theoretical aspects of mass transfer theories or mass transfer models. In most of the mass transfer operations, two immiscible phases are brought into intimate contact in order to permit mass transfer of substances between them. For example, distillation, absorption, liquid-liquid extraction, etc. Each of these processes is characterized by transfer of material across the interface. The rate of diffusion in each phase is dependent upon concentration gradient within it. When equilibrium is established, concentration gradients and the rate of diffusion will fall to zero. Whenever a substance is distributed between two immiscible phases, a dynamic equilibrium is established. Equality of chemical potential of solute, not concentration, which causes the net transfer of solute to zero. Therefore, it is necessary to study both the diffusion phenomena and equilibria in order to describe various situations fully. The rate of mass transfer between two fluid phases will depend upon the physical property of the two phases, concentration difference, the interfacial area, and the degree of turbulence. Several theories have been proposed in the past to describe the mechanistic basis of mass transfer, which provided the relation for mass transfer coefficient in the liquid phase. Mass transfer coefficient regulates the rate at which equilibrium is approached, and it controls the time required for the separation, which in turn decides size and cost of the equipment. So we'll consider two theories here. First one is film theory, second one is surface renewal theory. As for film theory, mass transfer coefficient is given by this relation. As for Higgs penetration theory, mass transfer coefficient is given by this relation, whereas as for Dunkworth surface renewal theory, mass transfer coefficient is given by this relation. None of the textbook has provided a complete derivation about these results. So in couple of next videos, we'll go through the complete derivation of these results. Here in this figure, uh, a component A from a gas mixture is transferred to the liquid phase here, and during absorption. So how this profile is look like, so represented here. So first component A in gas mixture diffuses to the interface, and where it is absorbed, and finally it diffuses to the main bulk liquid. So this figure is example of surface renewal theory, which will be discussed later. First, we'll discuss film theory, which was proposed by Whitman in 1923. Following assumptions were made. There exists a stagnant thin film in each phase close to the interface, which offers resistance to mass transfer. The rest of the liquid beyond film boundary is kept at uniform composition by agitation. Concentration profile in the film is linear. The mass transfer process across the film is regarded as a steady state process of molecular diffusion. Turbulent in the bulk liquid is considered to die out at the interface. The bulk flow term in Fick's law is considered to be very small, so this flux is can be given by this relation. Now we'll consider a case where mass transfer is from solid to a flowing liquid is taking place. So this is the figure shown here, in which this is the liquid solid interface, and this is a thin film, and this is the bulk of the liquid, and uh, making a cell balance here. So and input and output streams are shown here. So we can write here rate of solute input at x is given by this relation. Rate of solute output at here is given by this relation. Rate of accumulation is zero because it is a steady state case. rate of input absolute minus rate of output absolute equal to 0, dividing both sides by delta x and taking the limit delta x is equal to 0, we get following relation. And by replacing Na by Fick's first law and arrive at this equation, and after integrating two times this differential equation, so we get this relation where C1 and C2 are integration constant. So following boundary conditions are considered. So at x is equal to 0, at here Ca is equal to Cai, and at x is equal to delta here Ca is equal to Cab. So applying boundary condition in equation 1, we get this relation which is representing a straight line. So mass transfer through the film is constant at the steady state and is given by this relation here. Uh, from this relation, we get this relation, and if we compare this relation with convective mass transfer flux, then we find that mass transfer coefficient KL is equal to diffusivity by delta L. So, which indicate that mass transfer coefficient is directly proportional to the diffusivity. Here, hydrodynamic property of the systems are taken into account by film thickness delta L, which depends upon geometry, physical property, and agitation. Though this model is not very realistic, as experimentally KL is often found to vary as diffusivity to the power zero point 0.5 to 0.65, but it has advantage of simplicity. So that's all today. In couple of next videos, we'll go through the derivation of Higgs penetration theory and Dankworth surface neural theory.